Hello, my dear learners. I am Hemlata Nimje from JSPM Chera College of Pharmacy and Research. Here, I am going to present the factors responsible for shifting the vibrational frequency. So, here, I am going to discuss about the factors which are responsible for shifting the vibrational frequencies from their normal values. There are various factors. Among these, the first one is Fermi resonance or couple vibration. Second, hydrogen bonding. Third, electronic effect. Fourth, bond strength. And last, field effect. Now in this video, I am going to discuss about the Fermi resonance and hydrogen bonding. So first of all, we should aware about the basic value of the IR. You can see that the OH has a 3600, NH has 3400 and CH has 3000 centimeter inverse. Similarly, the other functional group has their basic values. Now first factors we will discuss is the Fermi resonance, or it is also called as coupling vibration. So what it is? It is an isolated CH bond which has only one stretching vibrational frequency, whereas the methylene group shows two stretching vibrations, symmetrical and asymmetrical. Because of the mechanical coupling on interaction between the CH stretching vibration in the CH2 group. Now, the asymmetric vibration occur at higher frequency or wavelength than the symmetric stretching vibration. These are known as coupled vibration because these vibrations at a different frequency than that required for isolation of CH stretching. So remember, due to this, symmetric and asymmetric vibration, coupled vibration take place at a somewhat different frequencies. Now next is, we can see the examples of CH stretching vibration which has the basic value of 3000 centimeter inverse. Here in the methyl group, stretching vibration take place symmetric and here asymmetric. If you see, there is a difference in the frequencies or wave number. Symmetric vibration will give a lower frequency and asymmetric stretching will give somewhat high frequency or wave number. Similarly in the methylene, CH bond stretching symmetric, lower frequency, asymmetric stretching somewhat high. It is near about 3000, but it is shifted lower wave number. So in this way, they will shows a two peaks. One peak is divided into two peaks. That's why it is called as coupled vibrations. Now next example, I would like to tell you about methyl bending vibration. Similarly, asymmetric and symmetric vibration is also take place in CH3 in bending vibrations. So there will be a two peak which will overlap with each other, showing only one peak at near about 1400 to 1450 centimeter inverse. Now similarly, this couple vibration also called as Fermi resonance. But what is the meaning of resonance? Resonance is the vibration of a large amplitude produced by the relatively large vibration. Means a coupling of the two fundamental vibration modes produce the two new modes of vibration with a frequency higher and lower than that observed in the absence of interaction. Interaction can also take place between the fundamental vibration and overtone or combination tone vibrations, and such interactions are called as Fermi resonance. So here including the resonance. If two different vibrational levels belonging to the same species have nearly the same energy, means a shifting of one toward the lower and other toward the higher frequency of. This can be seen with the help of this example. if you see the anhydride which has a carbonyl group, these carbonyl groups are undergoing the resonance. In this resonance, it shows a 2 peak, that is called as a Fermi resonance. This Fermi resonance is due to only and only carbonyl group, and in between the oxygen they shifted their electrons, so that one peak is at 1810 and another peak at 1760. So the one peak is divided into the 2 peak due to the Fermi resonance presence due to the presence of carbonyl group. In the second example, you can see for the primary amine where the NH group is present. As it is a primary amine, there are the 2 NH2 is there. So N is bonded with the 2 hydrogens, which will give a symmetric as well as asymmetric peak. The symmetric stretching shows at 3300 centimeter inverse and asymmetric shows at higher frequency, that is 3400. It means that the NH2 shows a 2 peaks. That means a single peak is divided into the 2 peak due to this symmetric and asymmetric vibration. That is called as a coupling vibrations or Fermi resonance. You can see in this spectra here NH2, it shows this single broad peak. The single broad peak is divided into the 2, and this area showing the 2 peaks, one symmetric and asymmetric. So 3300, 3206. Here the NH2 will going to show the stretching. So another example, another factor which are responsible for the change in the vibrational frequency is hydrogen bonding. Now we see what is hydrogen bonding. The stronger the hydrogen bond, the longer the OH bond. The lower the vibration frequency and broader and more intense will be the absorption band. Similarly, in the NH stretching, frequency of amines are also affected by hydrogen bonding as that of hydroxyl group. But the frequency shifts from amines are lesser than that of hydroxyl compounds. Because the nitrogen is a less electronegative than the oxygen, so the hydrogen bonding in amine is weaker than that in hydroxyl compound. Now you understand that nitrogen is a less electronegative than the oxygen. That's why the hydrogen bonding in amine is weaker as compared to the hydroxy group. That's why it shows a broad peak and NH2 shows a medium peak. In hydrogen bonding, there is an intramolecular hydrogen bonding which give rise to the broad band, while intramolecular hydrogen bonds will give a sharp and well-defined bands. So as you know, inter and intermolecular hydrogen bonding can be distinguished with the help of dilution. Now we can see that how these peaks will show. This is the very sharp peak which shows by the alcohol which is free, and this is the total broad peak at 3300, where the alcohol or maybe acids or some of the compounds which has the hydroxy group like phenol, carboxylic acid like benzoic acid, this type of the compound having the OH functional group will give a OH stretching and showing a broad peak. So here how the intermolecular and intramolecular bondings are present in hydrogen bond. So see the hydrogen bond hydroxyl group, free hydroxyl group, how distinct bond has well defined length and strength. They are the free hydrogen bonds. And here this is the dilute solution where the CCl4 solvent is used. So lots of the CCl4 means this is a very dilute solution. This is the alcohol which shows many kinds of hydroxy bonds of a different lengths and strength, and this lead to the broad absorption. Why? Because there is a formation of the intermolecular as well as intramolecular hydrogen bonding. Now, this oxygen and the hydrogen which is form the bond, these are called as intramolecular hydrogen bonding, and this is the intermolecular hydrogen bonding. As this compound is having the intramolecular hydrogen bonding, it shows longer bond as well as broad bond and showing the lower frequency. So, hydrogen bonding occur in concentrated solution, that is undiluted solution, having the peak is near about at 3300 centimeter inverse, while in dilute solution it may be a longer wavelength as compared to the strong solution. Now we can see this with the help of example. You can see that this is an intramolecular hydrogen bonding remains unaffected on dilution, and as a result the absorption band also remains unaffected. Whereas in intermolecular bonds are broken on dilute solution, and as a result there is a decrease on in the bonded OH bond. Now see, in the pure liquid which is concentrated, it shows the very broad peak, that is there is a OH intermolecular and intramolecular bonding is happening here, so it has a large absorption and this gives a percent transmittance area wide. Similarly, in the dilute solution there are the free alcohol shows a sharp peak, but if bond is present, OH bond, like in acid, it will form this broad peak. But in case of free OH group which has no intermolecular bonding or intramolecular bonding, we can say this very dilute solution shows a very small peak, so that it doesn't show any hydroxy group in the form of intramolecular hydrogen bonding. So this will be the distinguish between the hydroxy identification of the hydroxy group into the IR spectrum. Now we can see that this spectrum is for hydroxy group of cyclohexanol, shows the OH stretching in the concentrated solution near about 3400 to 3200. But if you see the another example of acid, here it is also showing a broad peak in between 34 to 3200 in cyclohexanol. It shows a 400 to 3200. And now in the acid, see, this is a butyroic acid, very broad peak and having a different broadness as compared to the hydroxy group in cyclohexanol. So acid will shows a more broad peak due to the more of a OH bond as well as the resonance between the carbonyl group and oxygen. So due to this it will shows a more broad peak, and this indicate that it is having the hydroxy group but which is attached to the carbonyl, that means acid is present. And in previous example, if you see this previous example, it is a cyclohexanol free OH group, there will be so sharp peak, small as compared to acid. So this is the distinguishing in between this acid and free alcohol. So here we study about the factor responsible for shifting the vibrational frequency. First, Fermi resonance, and second, hydrogen bonding. Now rest of the factor, that is electronic effect, bond strength and field effect, will discuss in the next lecture. Thank you.